Hello everyone. In last lecture, what we saw, we covered the topic of sieve algorithm, and after that, we did that smallest prime factor algorithm, like how we extended that sieve algorithm to find out smallest prime factor. So in this video, what we'll do, we'll learn the concept of divisors. We'll solve a problem of divisors, and after that, we'll take one more example of that sieve algorithm. Okay, which is related to a smallest prime factor. So you'll get idea how to solve such problems. So in last what we saw, we just covered the topic of prime factorization. Okay, so if I have a number like 26, so its prime factorization was 2 into 13. Okay, but when it comes to divisors, okay, when it comes to divisors, it will be like all numbers which divides 26. Okay, so it will be 1, 26, 2 and 13. Okay, these four are divisors of 26. So what we did here, let's take another example, like take 20. Okay, so what we have, if I have 1, okay, if I divide 20 with 1, I'll get quotient as q as 20. Okay, so a number is q into x plus some remainder. Okay, here in this case we have remainder equal to 0, so our n will be qx in form of qx. Okay, so if a number is in form of qx, so what we can say, q is divisor of n, also x is also divisor of n. Okay, so when I say 1 is divisor of 20, we can say 20 is also divisor of 20. Okay, because 1 into 20 is 20. With this formula we can say it. When it comes to 2 into 10, okay, 2 into 10 is 20, so 2 and 10 both are divisors of 20. After this, 4 into 5, okay, 4 and 5 both are divisors of 20. And afterwards what will happen, if you go to the 5, it will be 5 into 4, then 10 into 2 and 20 into 1, which is exactly the reverse of this upper half. Okay, so like last time also, I talked about this. Okay, when I tried to prove that why we have to go just till square root of n to find out is it prime or not. Okay, so here is the same case, we have to just go till square root of n. See, what is square root of 20, which will be around 4 point something. Okay, so I have to go till 4. If I'll go till 4, I'll get every other divisors of that number. Okay, if you have already watched that last video, I think in first video I covered this thing, like why we have to go till square root of n just to check the number is prime or not. See, now what I'll do, so my I will be from 1 to square root of I is less than equal to n. Okay, it's the same representation as we are checking I is less than equal to square root of n. Okay, so if n modulo I equal to 0, what does it mean? It means that, let's take a number, so we have 20, so for I equal to 1, 20 modulo 1 is 0. Okay, so if this is the case, So what I'll do, I'll print I. Okay, I'll write this. See, I equal to 1. Yes, it gives modulo with 20 0. Okay, now what we saw here, with 1 20 comes. Okay, with 2 10 comes, with 4 5 comes. So what we can do here, if see this formula, n equal to qi, let's take like this, we'll take like this. Okay, n equal to q into I, this. So if I have n equal to qi, okay, and my I is 1, okay, so my n will be q for the first case, and q will also be divisors. We already know that both are divisors. So okay, for I equal to 1, you'll not going to understand this. See, let's take I equal to 2. So n equal to q into 2. Okay, so q will be n by 2. Okay, what we know, q and I both are divisors. Okay, so we can represent q as n by 2, where what was 2, it was I. So actually what we can say from this formula, okay, mm, q equal to n by I. So what I'll do, I'll print n by I also, if this is the case, and by doing such loop we can get all those divisors. Okay, so only in one case, okay, in one case these both number will be the same. Okay, like we'll print a same number two times. What will be the case? The case will be when we have square root is a perfect number. Okay, like perfect integer, we can say perfect integer. Okay, so the square root of n is perfect integer. It's a perfect integer and it divides that number. See, like this, take any square. Okay, like take 16. Okay, if we'll take 16, it will be like 1 into 16, then 2 into 8, and then 4, 4 into 4. See, so in this code, when I will be 4, we'll check this condition, it will be true, and we'll print here 4. Okay, and here we'll print 16 by 4, which is exactly number 4. Okay, so to avoid this thing, okay, what we can do, we'll write this like this. Okay, first we'll print I. Okay, this is if condition. Okay, in the if condition we'll first print I, and if n by I is not equal to I, okay, if it's not exactly the same as the number, okay, I number, then we'll print that n by I. Okay, so this is the things. Okay, this is the thing. So see, now we'll code it. Okay, first what we'll do, we'll take a number as input. Then what we have to do, for int I equal to 1, we'll start from the 1. We'll go to till the square root of n and plus. And it will be the another condition like n by I is not equal to I, then only we'll print n by I, and in the end we'll print a new line. Let's take 20. Okay, see, 120, 210, and 45. Now we'll take for 16. 116, 28, and 4 is only one time. Okay, like what happens in some problems, you have to keep the count of these divisors. Okay, when it comes to take the count of divisors, what will happen if we'll take 4 two times, the answer will get wrong. Okay, so this was the basic code for it. Okay, now what we'll do, we'll solve a problem from CACS. Okay, it's counting divisors, and what it says, given n integers, your task is to report for each integer the number of its divisors. Okay, in this problem we need just count of the divisors. Okay, how many numbers are there, okay, which are divisors of some number x. Okay, for example, x is 18, the correct answer is 6 because its divisors are 1, 2, 3, 6, 9, 18. Okay, now you can see here. Okay, 16, what's the answer for 16? 5. And what we saw for 16, oh, I removed the code. Okay, if you can remember, the divisors for 16 were 1, 16, 2, 18, and 4. Okay, this was the output. So see, there are 5 numbers. Okay, in that question we don't have to count 4 as multiple times. Like we are not going to count it 2 times. So what we have to do, we have to use same logic here. Now see, we have n numbers which are till 10 raised to 5. Okay, so we have given n numbers. Okay, and the range of the number will be from 1 to 10 raised to 6. So see, hmm, see, we have n equal to 1 is 6. Okay, around 10 raised to 6, and no, it's 10 raised to 5 actually, and the x is still 1 is 6. Okay, and for each x we are whatever operation we are doing, it's still square root of x now. So what will be the time complexity for checking an individual? Okay, for a single number it will be square root of 1 is 6, which is 1 is 3. Okay, like 1000, and into 1 is 5. Okay, like we are doing for 1 is 5 numbers, so it will be around 1 is 8. Okay, in omega notation it will be O of n square root of x. Okay, where n is the size of that array, how many numbers we are getting, and x is the number itself. Okay, so we can see what we have 1e8 operations. Okay, and we can do it in 1 second. Okay, we can do it in 1 second, but we have to like optimize the code. Okay, we really don't need some anything. Okay, anything like when if there's a condition where we are using vector, it can cause problems. Okay, for vector there's always a dynamic allocation. Okay, after some time the array gets dynamically allocated. Okay, more space allocated gets. So what happens in those conditions, some extra times require. Okay, and it probably leads to TLE. Okay, but in this question we really don't need these things. Okay, like we are going to use a simple loop. Okay, see, what we'll do, we have n as an input. Okay, now for n times we are going to take some integer x as an input. Okay, for int I equal to 0, I is less than n, I plus plus, what we are doing, we have some x, and let's print divisors of x. Okay, now we have to write this function divisors, which will return the count of divisors. Okay, okay, so our answer is 0. Okay, like the count, actually the count of divisors, it's 0. So what we'll do, for int I equal to 1, I into I is less than equal to that x, I plus plus. If x modulo I equal to 0, we'll first increment the counter and we'll check if that x by I is not equal to I, then we'll again increment that counter. Okay, here what we are doing, adding I, and in this we are adding n by I if n by I is not equal to I. Okay, it's the same case, like it's handling the, let's say that example, what was it, okay, it was 16. Okay, in the case of 16, for the I equal to 4, n by I was 4 and I was also 4. So what happened, we really needed only one time count. Okay, so for that, this is the case, when x by I is not equal to I, then only we are going to add one count. So here we have to just return that answer. Let's run it for given test cases. See, 5 2 6. Let's submit it. Okay, it got accepted. So this was the like very easy question. Okay, you will sometime get harder versions which is related to divisors. The concepts are of divisors, but it will be more harder than this. Okay, where the sub problem will be this. You have to do this thing. Okay, now the concept of divisors is like a very little. Okay, it's not that vast. So now what we'll do, we'll solve this problem. Okay, like this is a medium level problem. Okay, why? Because of this only. Here we have n is 10 raised to 7. Okay, so applying that sieve. Okay, what we saw last time, the time complexity for the sieve. Okay, like now we are moving to the question which is related to sieve. Okay, in the starting of the video, what I said, we'll solve that question on divisors, and after that we'll move to the problem which is related to SPF. Okay, smallest prime factor. So here we have n which is equal to 1 is 7 range. Okay, so what we saw last time, that our sieve was O of n log of log n time complexity. Okay, so it will be literally around 1e8. Okay, I think the time complexity will go around this bound. Okay, so we are going to barely pass that Yes, we are going to pass that test cases. See, we'll try the code. If something runtime error or any time limited error will come, we'll try to resolve it. Okay. So first we'll see the question. Okay. What question says? So the question says the task in the problem is to write a number in a multiplication of prime numbers separated by x. Okay, the symbol of multiplication. You need to put the number 1 in this multiplication. Okay, the question is straightforward. Like you can see the test case of 1. Okay, when it says 1, it printed just 1. When it's 2, it printed 1 into 2. For 4, it is 1 into 2 into 2. For 8, it's 1 into 2 into 2 into 2. Okay, so actually what it is, it's prime factorization, 2 into 2 into 2. Okay, and for just case of 1, what we have to print, we have to print just 1. Okay, and in other case we have to print 1 and also the actual prime factorization. Okay, so see. Okay, so here we are going to use the concept of SPF. Okay, in last lecture what we saw, we are extending our algorithm of sieve to pre-compute what we are pre-computing, smallest prime factor, smallest prime factor. Okay, smallest prime factor of that number, like SPF of I will be smallest prime factor. Okay, so here what we'll do, take a number. mm, let's say it's 70. Okay, so it will be 2 into 5 into 7. Okay, this is the prime factorization of 70, but we have to print 1 into 2 into 5 into 7. So I really can't remember I have covered this thing or not in last video. So if we have a 70 and its SPF of 70 is, it will be 2. Okay, 2 is the smallest prime factor. So if I divide 70 by SP of 70, so the next number I'll have, it will be the 35. If I'll check the SPF of 35, it will be the 5. Okay, the next number in the prime factorization. Like if I'll write the prime factorization in the ascending order, okay, 2, 5, then 7. Here what we can see, we got 5. If I divide that 35 with SP of 35, which is 5, what will be the next number? Next number will be the 7. And SPF of 7 is of course 7. Okay, 7 is the prime number. Its smallest prime factor will be the 7 itself. So we got this also. Okay, and when I divide 7 by SP of 7, the answer will be 1. And this is the point where we are going to stop. So what I want to say is, with the SPF, okay, SPF array, we have smallest prime factor of every number. We can actually get the prime factorization of that number. Okay, I think I covered this thing in last video. Okay, I hope you understood this thing. Okay, so in this question what we'll do, we'll do the same thing. Okay, the same thing we did here. First pre-compute SPF array. Okay, we are going to use that sieve algorithm to have SPF array. After that, what we'll do, we'll take input of that number. Okay, we have multiple numbers. we have to take input till end of the file. Okay, in the question they didn't specified about like how much input we have to take. Okay, we have to take until the end of the file. So we'll take input, and on that input we'll do this thing. Okay, and yes, see, in this question they didn't specified about like the order in which we are printing should be ascending or descending. Okay, like I really don't know a random order will pass the test cases or not, but see, when we are doing this procedure, okay, this procedure we are covering it in ascending order. Okay, so if even that is the case, our code will pass. Okay, so we don't have to worry about this. And in third step, what we'll do? Okay, this will be the third step after taking the input. So let's try to code it. Okay, so what I actually need these things. Okay, like every number, I need every number. So first thing is we have to take input, and we have to take input till the like till the end of the file. It means that we have to take input like in C++. What we do, we'll write like this, scene of x. Okay, like this code will run until we have some x to take input. Okay, so now we have input of x. Before that, what we need, we have to pre-compute. And if you'll see what we have as a size, the max bound, it is 1 is 7. Okay, so I'll make a SPF array of size of n. Okay, so first what we need to do, we have to assign by itself. What we'll do, we'll assign by itself, like uh, for any prime number. Consider we have 2. The smallest prime factor of 2 is 2. Then we'll move, let's take another random number, 97. Okay, 97 is the prime number. So the SPF of 97 will also be the itself 97. Okay, so what we'll do, will the way in C, what we did first, what we considered that all numbers are prime, and we traveled in the loop, and after traversing, what we did, we removed the divisors, sorry, multiples of that number. Okay, so same thing we'll do here. Okay, a minor change. What we'll do, from I equal to 1 to I is less than n, I plus plus SPF of I equal to I. Okay, now mm, we have to do sieve algorithm here. Okay, from int I equal to 2, I is, okay, I into I is less than equal to n and I plus plus. Okay, then if, okay, now after doing this thing, okay, here we initialize this thing. So what we have, if SPF of I equal to I, what does it mean? It means that I is prime. Okay, except 1. Okay, except 1, we are assigning 1 as a 1, but it's not prime number. Okay, we know that. So we are starting loop from 2, so we really don't need to handle the case of 1. Okay, so if SPF of I equal to I, Now what we are going to do, we are going to assign all the multiples of that number as I. Okay, SPF of j will be I if and only if it's like we haven't assigned any SPF to it. Okay, see, let me write the condition. So for in j equal to I into I, we know that we have to start from the square of the number. Okay, then j will be the less than n and j plus equal to I. So if SPF of j equal to j, okay, then only will assign SPF of j equal to I. So here what does this mean? If SPF of j equal to j, it means that we we never cut down that number. Okay, we never cut that number. So the current I is the first number in order. Okay, first number in order, which is dividing that j number. Okay, so if this is the case, like we haven't cut that j before, okay, anytime before, like see, mm, let me erase, see, so we'll take a small case here. Okay, 1 2 3 4 5 6. So what we are actually doing, for 2 we'll assign 4 SPF of 4 equal to 2, SPF of 6 equal to 2, and when we are traversing for 3, okay, 3 will reach to the 6, but now SPF of 6 is 2 and it's not 6. Okay, so if SPF of 6 is not 6, what does it mean? That we already assigned some smallest prime factor to this number. Okay, if we already assigned some smallest prime factor number, how can a number which is greater than that previous number will be the smallest prime factor of the number? Okay, so we can't reassign 3 here. So this is the case here. So now after this loop, what we have smallest prime factors, okay, for every number. Now we have to just print. Okay, so first we have to handle 1. Okay, like we have to always print 1. After that, while SPF of x is not equal to 1. Okay, 1 is the end. Whenever the SPF of x will be the one, we have to break out. Even we can say x is not equal to 1. Okay, when x will reach to the 1, we have to stop. Now what we have to print, we have to print SPF of x. Okay, then we need an x and space. Okay, we have to print output in this format. Okay, now what we did last time, if we have to find next prime factor, what we did, we divided that number with its SPF. So x by equal to SPF of x, and after this loop we have to print a new line. Let's see, is it working for the given test cases or not. Oh, Control X. See, the output is correct. So what we'll do? We'll submit this. Oh, okay. What we got? We got time limit exceeded. Okay. So what is actually happening? Even we optimized it. Okay, like we used a static array here. Okay, we didn't use that vector. Okay, despite we got a TLE. Okay, so the problem is the cin. Okay, cin takes more time. Okay, cin cout takes more time than scanf and printf. So what we'll do? We'll use scanf here. %d and x, and what we'll do is not equal to end of file. Okay, what this thing will take input of x until we'll reach to the end of the file. Okay, see, it's accepted. So let's let's try this out. Is it possible? Scene of x is not equal to end of file. I never tried it. Okay, does it work like this? No, it doesn't. I hope you understood this question. Okay, because of time bound, what we did, we just use scanf instead of scene. Okay, because scanf is faster. Why it's faster? That's your homework. Explore that thing by yourself. So I think that's it. That's it for today. Uh, in next, what we'll do? What we can do? Okay, we'll move to the GCD and LCM. Okay, we'll cover those topics, and if required, I really don't think there are much problem should I take on this topic. Okay, you can explore by yourself. Okay, there are so many websites where you can practice. Okay, here are some. Okay, see, this. Okay, this is one of the best topic list. Okay, you'll find in number theory that save prime factorial divisors. If you'll open it, you'll see more resources to explore and then solve these problems. Okay, there are so many problems you can solve. You'll learn so many things. Okay, I'll add this link in description of the video and you can explore. Okay, there are basic things also, and another is programmer.one. Okay, currently server is down, but this is one of the best compilation of the problems. Okay, Programmer.fun, and the ultimate topic is choose anyone, okay, and try to solve those problems. So I think that's for it today. Bye.